Hello everyone, welcome to Mechanics of Fluids tutorials. So in this video I would like to explain about loss of energy. I would like to explain about loss of energy or loss of energy or head due to an obstacle, due to an obstacle or obstruction, due to an obstruction in a pipe, due to an obstruction in a pipe. Okay, this is also minor loss. So here whenever any sudden obstacle takes place in a pipe flow, automatically some loss of energy takes place. So how to find out that loss of energy due to an obstruction means here, first assume a pipe which is of particular diameter. Okay, so in which the water is flowing with certain velocity v. Okay, assume, and here suddenly a particle solid body has came into place. Okay, so due to this obstacle, certain loss of energy takes place. Why? Because means whenever it is suddenly striking, so after striking it will try to flow over the solid body. So when it is flowing over the solid body, the variation in the cross sectional area takes place due to the sudden change in energy. So already we know that when a water strikes a solid body, the loss in momentum takes place, which causes the energy loss. And similarly when it strikes the solid body, the cross sectional area variation takes place, which again causes the loss of energy. So during that loss of energy, so water will try to reduce its cross sectional area over the body, that is the solid particle which is an obstacle. So like this separation of the water takes place up to particular distance. So variation in the cross sectional area for the flow of the water takes place, and slowly it will reach the maximum area condition, and after that again it will lose the effect of the solid body. So again the variation in the cross sectional area takes place in the form of the enlargement in the cross sectional area. Like this the water will be flowing over the solid body like this. Okay, so again here we can observe one more condition here. At a particular point it is reaching certain minimum area condition, that which we can consider as a vena contracta. So I'm assuming as section C. So from this vena contracta again the enlargement in the cross sectional area is taking place, and again it is reaching the same cross sectional area of the pipe. So in this condition also the loss of energy takes place. So here whatever the loss of energy has taken place at the obstacle, the same loss of energy takes place during the enlargement in the cross sectional area of the flow from the vena contractor to the pipe diameter. Okay now, so that means, so by this analysis we can say that whatever the loss of energy, we can say that loss of energy, loss of energy due to an obstacle, due to an obstruction, due to an obstruction, okay, due to an obstruction can be equal to, due to an obstruction can be equal to loss of energy, loss of energy due to enlargement, due to enlargement, due to enlargement from vena contracta to the section 2. Assume here it is section 2. Okay, so whatever the loss of energy is taking place at an obstacle, so the same loss of energy takes place from vena contracta to the section 2, which is again the diameter of the pipe. Okay, so assume represent the symbol with HOBS, that is the loss of head or energy due to an obstruction is equal to loss of energy due to enlargement. So from C to section 2 means here assume at the vena contracta velocity as VC, and here again the velocity becomes equal to the velocity of flow only. So already we know the formula for loss of energy due to friction is V1 minus V2 whole square by 2G. Similarly here V1 is VC and V2 is V, so we can write it as VC minus V whole square by 2G, we can write it as. Okay, so like this we can write the equation for the loss of energy due to an obstruction present in the pipe flow, but still it is not a sufficient formula to find out the loss of energy due to the obstruction. We can modify the equation by, how can we modify the equation means, here I would like to write the continuity equation. I want to write continuity equation in between section C and section 2. So continued equation, how can we write? Already we know that A1 V1 is equal to A2 V2. Similarly, AC VC is equal to, we can write it as A and B. Okay, so in this equation try to write VC is equal to AB by AC. Okay, still it is in the form of uh, area at the vena contracta. So this area at the vena contracta again we can modify by considering the coefficient of contraction. So try to write again coefficient coefficient of contraction coefficient of contraction. So what is the definition of coefficient of contraction? It is the ratio of area at the vena contracta to the area of the pipe. Okay now, so area at the vena contracta, here we can assume, already assumed as AC. Okay, and area of the pipe as A only assume. So already we have written here AB and AB. So we can write here area at the vena contracta. Okay, so the coefficient of contraction can be defined as the ratio of area at vena contracta to the area of the pipe. Okay, CC is equal to, so again AC is equal to, we can write it as, sorry, here area at the vena contracta to the area of the flow which is causing the variation in the cross sectional area. So here, so how the vena contracta we are getting here due to the obstacle present. Okay, now initial condition for making the vena contracta, initial area condition is which is the flowing, which is the flow is taking place over the obstacle. So here over the obstacle, so what is the area of the flow is taking place? That means here if you assume area of the obstacle as a small a, okay, now then the after striking, the cross sectional area of the flow will be a minus a, above and below. Okay, we need to subtract the small a. So here the area at the vena contracta to the area of the cross section of the flow after striking the solid body. So after striking the solid body only we are facing the area of contraction. So the area at this section C to the area at the obstacle, that is the obstruction present, the ratio of these two will give you the coefficient of contraction. So AC again can be written as CC into capital A minus small a. Okay, so this is the equation we got for AC. So again substitute this AC in the above equation. Okay, so now VC is equal to, we can write it as VC is equal to AB by CC into capital A minus small a. Okay, so again substitute this VC value, that is the formula in HOBS obstruction. So which is HOBS is equal to, already we have written as VC minus V whole square by 2G. So in place of VC, write down that equation AV by CC into capital A minus small a minus V whole square by 2G will be getting after substituting that equation. So in this equation again take V square by 2G as common. So take V square by 2G as common. So in the numerator we have to take the common of V square. So the V term will be eliminated. So we can write it as A by CC into capital A minus small a whole minus 1 whole square. Okay, so this is the equation for finding the loss of energy due to an obstruction, which is in the form of velocity of flow and the area of the pipe and the area of an obstacle. Sorry, here I forgot to write 1, so minus 1 whole square. Okay, this is the final equation which is used to find the HOBS. Again I would like to write the formula. So HOBS, obstacle loss of energy or head due to an obstruction, is V square by 2G. Okay, 2G into A by CC into A minus small a minus 1 whole square. Okay, this is the equation for finding the loss of energy due to an obstruction in a pipe. Okay, I hope you understand the simple derivation for finding the loss of energy due to an obstruction in the flow of the fluid. Okay, and once again thanks for watching my video. Thank you all. If you like my video, please subscribe and share my videos with your friends. And if you have any doubts regarding this mechanics of fluids, any topic, please give a comment to my video so that I prepare a video and I'll try to upload. And once again, thanks for watching my video. Thank you all.